So for this lecture, we're going to look at taking the simplex method a little bit farther and something called artificial starting solutions. So artificial starting solutions comes into play when you need to find a starting point for your simplex method where the normal starting point doesn't work. So the simplex method works. It's a very powerful method, but it does have a limitation in that because it works by jumping from corner to corner in your feasible region, you have to start at a corner in your feasible region. The examples we've seen up to this point, we start with a point where all of the variables are equal to 0, but sometimes that's not in your feasible region. So for instance, in this first example, you can see if you plug in x1 equals 0, x2 equals 0, you get a feasible point. It satisfies all of the constraints. This works nicely if all of your constraints are less than or equal to's and all of your coefficients are positive. But that doesn't always happen. Sometimes you have constraints that are less than or equal to constraints. Sometimes you have constraints that are actual equality constraints. In those cases, and if you look at this example, you can see the point 0, 0 is not in the feasible region. It's violating constraints. So in order to apply the simplex method in this case, we first have to find a point that's in the feasible region. And that's where introducing artificial variables gives us that starting point. So an artificial variable is used where we need a starting point that's in the feasible region, but the point where all of the variables are 0 is not a feasible point. So what you're looking for, or the goal with getting the artificial variables, is to create a positive variable with coefficient 1 that appears in only that constraint. Now, if you remember when we were doing slack and surplus variables, slack variables satisfy that. Surplus variables don't, because they have a coefficient of -1. So if you take this example here, and you add in your surplus variables here, which you need because you're dealing with greater than or equal to constraints, we don't have that condition. And if you try to plug in x equals 1, x1 equals 0, x2 equals 0, you see it's not a feasible point. So what we do is we add the artificial variables, in this case, a and b. So you can see now that if you take your point, if you take all of the other variables, x1, x2, r, and x, make them equal to 0, you now have a feasible point. You have to set a equal 2 and b equal 4, but you have a point where all of your other variables are equal to 0, and it's a feasible point. So now we have a place to start with this new linear program. We've changed our original program, added something else in there, and we now have a feasible point we can start at. The problem is this is not the same linear program because we've added extra things. What are these artificial variables that we've added? So in this example, the a and b that we've added. In some cases, if we have a constraint that's an equality, we add it in, but we have something that's equal and then we're adding in an extra variable. In other cases, we have a slack variable or a surplus variable that's in there, and then we're adding in this extra variable. What does it do? Well, it's just in there as an artificial construction to give us a starting point. But when we optimize, we need to make sure that at the end of the day, those things are equal to 0. If you go back and look at the problems and you imagine that you have an optimal solution, those a's and b's had better be equal to 0, otherwise you are going to violate your constraints. So we're going to have to adjust our linear program to guarantee that a and b equals 0. We've found a place to start, but we've changed our linear program a little bit. But we can get back to our original linear program if all of our artificial variables are equal to 0. So we're going to try solve our updated problem and force the a and b equal to 0. And we have two methods to do this. They're called the M method, or the big M method, and the two-phase method. So let's look at the M method first. And remember, keep in mind here, our objective is to take our updated linear program and to make our artificial variables to force them to be 0. So one way to do this is with something called the big M method, where we're going to introduce those artificial variables into our objective function, but we're going to make them very large so that they dwarf everything else in there. So here is the linear program that we got by adding in our artificial variables. If you were to just solve this, you would end up with positive values for a and b. That's not what we want. We want to force a and b equal to 0. So what we're going to do is we are going to add those variables into our objective function, make them negative, and we put this m in front of them. This m represents an incredibly large number. So when we're solving our linear program, m times a is going to dwarf everything else. We make it negative, so if a is even the tiniest value, it is going to make the entire objective function very large and very negative. So the idea now is that when you solve this with the negative ma minus mb in there, a and b are going to be forced to be 0. Otherwise, you're going to end up with a very large negative number. So how do we do this? Well, if we take this, so with the idea that this new objective function is going to force our a and b equal to 0, we take this and we can put this into a tableau. But notice we have a bit of an issue with our tableau. When we played with the simplex method before and we looked at our slack variables, we always had that the slack variable had a value in the objective row of 0. So we have to make another adjustment to our objective function first to get a 0 in those columns. So how do we remove those variables from our objective function? Well, we have, if you look at our constraints, now that we've added in the artificial variables, those are equalities. So we can rewrite them, in this case, as a equals something and b equals something. And we just take that a and b and substitute it in for where you see the a and b in your objective function. What's that going to do? You're just doing a simple substitution that removes your objective or your artificial variables from your objective function. So it turns that new objective function into something that deals with only the other variables. And once we've done this, we can put it back into the tableau and we'll have the form that we need. So when we put it back into the tableau, notice now that our a and b have 0 values in the objective row. That's what we're looking for. Now we can solve this. But how do you solve this with these m's sitting here? Because those m's get carried over to the other variables when we did the substitution. Well, again, just think of them as very large numbers that dwarf everything else. So if you look at this, we have plus 4m, that's going to dwarf everything else. This is plus m, but what we're looking for is the largest negative number. This is a negative m, that's a negative m. You can choose one of those two for your pivot column. And then from that point, once you've chosen your pivot column, you just continue your simplex method all the way through, carrying those variables through until you get all positive numbers on your top objective function, the same way as you do your normal simplex method. If the problem is infeasible, sometimes you will do this, and one of those artificial variables will be a basic variable. In other words, it'll be on the left-hand side. What does this mean? This means that the problem is infeasible. When you get a basic artificial variable on the left-hand side, you have an infeasible problem. So for instance, if you take this problem and you solve it out with the big M method, you are going to see that you end up with an artificial variable on the left-hand side when you have your optimal solution, when the simplex method says you're finished. What does that mean? That means that your artificial variable has a positive value. And remember what we're trying to do here. We are trying to get artificial variables equal to 0. If they have any positive value at all, then they don't satisfy, then the result you get does not satisfy your initial problem. So if your artificial variable ends up as being basic, then you have no solution. Okay, so I mentioned that there were two methods, the big M method, and the second one is the two-phase method. This is essentially the same thing. It's the same thing that's going to happen in the background as with the M method. It just represents it a little bit differently. So in this case, we don't introduce those additional variables of unknown size. The big M is gone. We're going to deal with just the numbers that you have in your linear program. So here's an example. Here is our original problem, which we've taken and we've converted over to this. We've noticed we have surplus variables in each one, so we add an artificial variable. We still do have the artificial variables. So that's the same as before. But now, once we have the artificial variables, remember that the objective now is we want to solve this and make our artificial variables equal to 0. So what we're going to do is we are going to find a point that is feasible where the artificial variables are equal to 0. That's what we need to have for a starting point for our simplex method. So we are going to forget about our objective function for this point, because what we need is just anything where our artificial variables are equal to 0, but is a feasible point. So we are going to change our objective function to say that a plus b equals w, and we want to minimize it. So think about when this happens. This happens when a equals 0 and b equals 0, because a and b in our new problem have to be positive or non-negative. When are they minimized? When they're 0. So now we have another linear program very closely related, the same constraints, but we've replaced our objective function to get us where we want to go. So we take our objective function and we change the minimize to a maximize by making it a negative, because the simplex method that we've done so far is for maximization problems. And we can create a tableau. But now notice we have the same problem that we had with the M method, in that the values, the coefficients in our objective function for our basic variables are non-zero. So we have to do the substitution. But the substitution in this case doesn't involve this huge value M. We have actual constraints that are equalities. From those we can get a equals something, b equals something. Substitute them back into our objective function. We end up with a new objective function written in terms of all of the other variables. So we've taken our artificial variables out of our objective function. Same way as we did for the M method, just our objective function is a little bit cleaner. And now we can take that and we can put it into our tableau, and we've got the form we need for it. Now, notice that quite often when you do this, two things to notice here. Usually when you do this, you are going to end up with a solution that is non-zero. It's going to be less than 0. What you're trying to do is to get that to 0. Now, another thing to note, when we went from our first tableau to our second tableau, we did substitutions. We said let A equal something, let B equal something, and put them back in. Think back to our linear programming, elementary row operations. Now take a look at the matrix we have here in the tableau, where we say that our objective function, we're going to call that row 0, and all of our other ones we call row 1 and row 2. So row 0, row 1, row 2 going down. Now take our first one and look at this elementary operation, elementary row operation. It's actually a couple of elementary row operations strung together. Row 0 minus row 1 minus row 2 gives the new row 0. Well, if you do that, you'll see that that gives you exactly the tableau. Now here's a point that is going to come up a little bit later in the course. When you're doing substitutions, when you're doing pivots, you're really just doing matrix operations. When you do a substitution, as you saw in linear algebra classes, when you do a substitution, you are really just doing a matrix operation. It's the same thing with tableaus. Okay? So that's just something to note for later. What we're doing is we're doing a substitution. So now we have a tableau that's in the form we need. We have a starting feasible point, because if at this point A and B are our basic variables, so A equals 2, B equals 4, our other variables, x1, x2, r, and s, you set them all equal to 0, you have a feasible point. That's what we need for our simplex method. So now we can solve this linear program using this tableau. Again, choose your most negative value, choose your lowest ratio, that's your pivot point, start pivoting. Do your pivot a couple of times, and you will end up with this new tableau. With this tableau, what do you have now? x1 equals 10 over 7, x2 equals 2 over 7, r and s equals 0, a and b equals 0, because they are non-basic variables. Take this and put it back into and look at it in terms of your original constraints. This point, x1 equals 10 over 7, x2 equals 2 over 7, r equals 0, s equals 0, a equals 0, b equals 0. This is a feasible point back in your original linear program. That's what we need. We now have a point that we can go back to our original linear program, start from that point, and solve our simplex. Let's solve our linear program using our simplex method. Now, one thing to note here, this is the end of phase 1. The objective of phase 1 was to find a starting feasible point for your simplex method. To do that, we built the artificial variables, and we said we have to make these artificial variables equal to 0. So at this point, we have a solution after phase 1 that is equal to 0. If you can't get there, if you can't get that solution equal to 0, that means that either A or B is non-zero. That means you do not even have a single feasible point in your region. It means that your constraints contradict each other. You have no feasible region. So at the end of phase 1, make sure that your solution is equal to 0. Because remember, we built this by saying we're minimizing A plus B. If we can't make A plus B equal to 0, we do not have a feasible region at all. There are no feasible points. But assuming that we have found a feasible region, that we are able to make our solution equal to 0, what do we do now? Well, now we go back to our original function. That was our original objective function. A and B have done their job. They were only there to get us to a feasible point. So now we can take those two columns and just drop them. And we get a new tableau dealing with the points that we're interested in. But now we have that same problem that's cropped up a couple of times. Our basic variables are x1 and x2. Usually when you do this, you will end up with those being in your objective function, and you don't want those in your objective function. So we have to do that substitution again to get them out of our objective function. So let's take this tableau and write out the linear program for it. This is the tableau that we got when we dropped our A and B. Here is the linear program we get when we write it out. Notice our basic variables now are x1 and x2. x1 and x2 exist. Each one is in a single constraint with a coefficient of 1. So we can rewrite a constraint as x1 equals 1 over 7r plus 2 over 7s plus 10 over 7, for instance. And we can substitute that back into our objective function. Do the same thing for x2. We want to get our basic variables out of our objective function. We end up with a new constraint, a new objective function. Well, it's the same objective function, but we've written it now in terms of our non-basic variables, which is what we want. Take that and put it back into our tableau, and we end up with a new tableau in the format we want. Now, I'm going to point out, note that you can also do this with elementary row operations. If you take this initial tableau up in the top left corner, and you do row 0 minus 2 row 2 minus 3 row 1 is the new row 0, you will end up with exactly the top line you get in your updated tableau. So substitutions are just row operations. But now we have a tableau that we can use our simplex method on. Now remember what the simplex method is. Find the most negative number and pivot. Find the most negative number in your objective function and pivot. Notice in this objective function, we don't have a negative number. And that's fine. That means that at the end of phase 1, we found a feasible point, and that feasible point just happens to be the optimum value. Quite often you will have to do more pivots, because now all you've done is you've found a corner. That corner might or might not be the optimum value. Sometimes you have to pivot to jump to other corners. In this case, we're done. We've found our optimum value. Okay, now there is one complication you can get with the two-phase method. Sometimes when you're at the end of phase 1, you found that your total, your solution is 0, so that number in the top right corner is 0, so it looks good, but one of those artificial variables will still be a basic variable. When this happens, you will note that the value of that variable is equal to 0, so the far right line, so A will be in the left column, the corresponding entry in the far right of your tableau will be 0. You have to do another pivot to get that artificial variable out of your set of basic variables. Okay, so this is something that doesn't happen all the time, just every once in a while it happens. So what you're going to do is you're going to do a pivot. You are going to select a 0 artificial variable that's in the basic, that's in the basis, that's on the left-hand side, and you're going to pivot someplace in that row. And to do this, you just pick any number in there, any value in there, any column that is not an artificial variable, and you just pivot on it. Sometimes the value you're pivoting on here will be negative, but you just follow the same rules for pivoting as you normally have. Then, once you've done that, you can actually take that column right out, rewrite your tableau. If all of your artificial variables are non-basic, you're good. You're finished phase 1 now. If you still have an artificial variable that is basic, you have to do this process again. But you just keep doing this until all of your artificial variables are non-basic, that they're out of that left-hand column. So this is just a complication that comes up every once in a while. So that's a look at when you have to introduce artificial variables. And the reason you have to introduce artificial variables is that sometimes your linear program does not give you an easy, feasible solution to feasible point to start with. This happens when you have greater than or equal to constraints or you have equality constraints. You introduce the artificial variables. You optimize first to set them equal to 0. You have to get those artificial variables equal to 0. What you get then is a point that is a feasible point, and now you have a point that you can start your simplex method from.